Hi, my name's Claire Techlitz. I'm the scrub master for the Girl Gang, which is group B3, and for this project we made an injection molder.
So our problem was that we needed to be able to heat plastic to its melting point and then inject it into a mold in order to quickly make plastic parts.
So some objectives for our injection molder were to be able to heat it to the correct temperature, which is about 220 degrees Celsius, to be able to plunge all of the material out, at least about 90% of it, with one plunge. Also to do that with limited operator force, so a human kind of on average is about 30 newtons whenever they push, and so less than that, that's why we're using a jack, except with common thermoplastics like PLA or ABS.
Our budget was set to $240. We were limited on time because we only met 2 times a week for 12 weeks. Plastic had to be able to reach 220 degrees Celsius. We had to be able to inject 100 cube centimeters of plastic. The overall mechanism needed to be between 20 to 40 pounds so that one person could easily carry it. We wanted limited operator force to be within 30 newtons per person, so we chose a jack to help us reach that goal. The overall process needed to be short, so we chose 16 minutes for the heating, injection, and cooling of the plastic. One of the heating mechanisms to operate on a standard wall outlet, receiving roughly 10 amps.
Our injection molder was intended to create a useful butter knife. Shown here on the right is the SolidWorks model of the knife, and on the left is the actual mold after it was CNC'd. The furthest our injection molder ever got was pushing plastic out of the nozzle, which technically is the job of an injection molder.
The electronics in this prototype are controlled by a PID controller. The PID controller takes user input to set the desired temperature and also shows a reading of the measured temperature by the thermocouple. The thermocouple is connected directly to the PID controller. The PID controller also connects to the solid-state relay, the heating bands, and the 120-volt wall outlet.
To verify that the plastic reached the desired temperature we needed to get it to melt, we ran a SolidWorks simulation for a transient thermal simulation. We set the outside of the tube to 300 degrees and ran the simulation, and were able to discover that it took about 12 minutes to melt the inside of the plastic.
This simulation was useful because it modeled a worst-case scenario. It used a solid cylinder of plastic instead of loose pellets. We also checked this experimentally. We heated up the heating chamber without the mold, and we discovered that it took 15 minutes for the plastic to be viscous enough. We checked this with a metal rod. We performed a statics analysis on the design from precious plastics to determine the force applied by the man in the video. We also determined the force using the Bernoulli's equation using the desired flow, and it was determined that the force was greater than what we could easily apply by hand.
One of our constraints was the time we spent on the project, which was the goal of 6 hours per person. At the beginning of the project, we really only did in-class time of about 4 hours a person, but towards the end, we got up to 6 to 8 hours per person out of class time, doing welding, machining, extra testing trials, epoxying, the whole thing. Another constraint was the plastic temperature. So we wanted to heat up our plastic to 220 degrees Celsius. We typically heat it up to about 210. However, our thermocouple was outside of the pipe, so the inside of the pipe was much hotter than 220 degrees, and we were definitely able to heat up the plastic enough. We also wanted to keep within our budget, which was $240, which we were able to stick to, due to some free material from Buddy and just kind of being resourceful. One of our goals was to keep the size of our injection molder desktop size. Unfortunately, we didn't meet that goal. We made it a little bit bigger than we needed to. We had a couple issues with materials and welding, and so in the end, it was actually very heavy and it's pretty big, so it doesn't really fit to be desktop size. Our last constraint was the amount injected. We wanted to inject about 100 centimeters cubed of plastic. Unfortunately, we weren't able to get that. We were able to inject a very small amount, I'd say probably half a centimeter cubed. We didn't inject the amount we wanted to, but that was one of the constraints we weren't able to make.
So most of our issues came from the quality and the type of part that was received. Our heating chamber came with a weld in the middle, which is difficult to get a correct fit. So we spent a lot of time fixing this. So next time we would perhaps not order from Amazon. We also received a plunger that was not the correct diameter. So we spent a lot of time using washers attached to the end to try and fix it. So in the future, from the start, although it costs more money, we should just get a new plunger. That we should use better connections than thermal epoxy, use threads next time, or use welding, because we had a lot of problems where the thermal epoxy failed. We should try to maximize the size of the hole that goes into the mold, because we had a lot of issues getting plastic to come through the bottom of the tube.